Alright, it's been so long since I last made a video, I now wear glasses. Isn't that crazy? Alright, so in this video we'll be talking about reference circles and how we can use it to track the motion of an object in simple harmonic motion. Now, like I said in the intro, the point of using reference circles is to make our lives easier when we're trying to track the motion of an object in simple harmonic motion. So we want to track the motion at time t. Right, so at any given time, we want to know the displacement, the velocity, and the acceleration of the object that is in simple harmonic motion. A common example that you would get of something that's in simple harmonic motion is a pendulum, right? Like this. And this pendulum is moving left to right. Right, where this is the mean position, the middle position. Now, the nice thing about simple harmonic motion is that the motion follows the path of a trig function. So first off, I'm going to go over a quick recap on how the trig function applies to simple harmonic motion. So let's say we take this pendulum, right, and we go from the mean position, and this pendulum is still moving left to right. At the mean position, the x displacement is 0, right? Where x is the horizontal movement. And so if we were to graph this, right, with our x displacement over here, right, this is our x, and this is the angle theta that it moves through, right? The pendulum moves through, right? So that would be theta right here, okay? Right, so this is x, and then this will be negative x, right? Like I said previously, when we're at the mean position, x is equal to 0. So we're going to start over here at x is equal to 0, right? Then let's say it moves this way. So as it moves that way, it's going to go to max displacement, right? So max displacement is up here, right? Then we know it's going to come back to the mean. So that means it's going to come back right here. And then it's going to go this way to max displacement again, however, in the other direction. So this is actually negative max displacement, right? So that is down here. And then it's going to come back to the mean, after which it's completed one period. So we go back here. And as you can see, if we follow this path, this follows the path of a sine curve, right? Now, alternatively, if we were to start, rather than starting from the mean, we start at max displacement, okay? We can do the same thing, where we have our graph, where this is theta, this is max displacement, and this is negative max displacement. We are starting at max displacement, right? So if we imagine a pendulum, where we're holding it up to max displacement, and then we let it go, right? So we start at max displacement, so we're starting here. It comes down to the mean position, right? Goes this way to negative max displacement. Comes back here to the mean. And then back up to positive max displacement. Like so. And as you can see, this follows the path of a cos function, right? So this is cos theta, and this is sine theta. So keep that in mind. If we're starting from the mean, when we're talking about displacement, we use the sine function, and then when we start from the max displacement, we use the cos function. However, the sine function on its own is not going to work very well, because sine theta gives us a value between 1 and negative 1, right? So let's say our amplitude is equal to 1.4 meters, right? Where our amplitude is actually our max displacement, right? So we can say our amplitude, which is also A, right? We can say that's A, and we can replace that over here if we want, right? So we can say this is A, and this is negative A, okay? So amplitude, max displacement, same thing. If our amplitude is 1.4 meters, and we just type in sine theta, and it gives us a value between 1 and negative 1, that's not very helpful, right? But instead, how about we do amplitude times sine theta, right? Now, if we know that sine theta gives us a value between 1 and -1, and we multiply it by our amplitude, if sine is 1, then we will get our max value over here. If sine is -1, then we will get our minimum value, negative amplitude. And if sine theta is any value in between, let's say 0.3, it will return a value somewhere in the middle. So now our equation, x of t is equal to a sine theta, is slightly more helpful. However, theta, what is theta? It's an angle at which the pendulum has turned through, right? This is theta. So how do we work that out? Because as I said in the beginning, we're trying to track the pendulum at time t, not at a certain theta value. We're trying to find at time t, okay? Now, if you recall, one period on a pendulum is when it goes from its starting position, let's say the mean, goes to max displacement once, comes back to the other max displacement, and then back to where it starts, right? And so, like I said before, that tracks this motion, right? We're starting from its mean position, coming up to max displacement over here, going back to the mean, negative max displacement, back to the mean. So this is one period, right? Now let's say we have an amplitude of 1.4 meters and a period, which is t, of 0.8 seconds, okay? So if we know that this is one period, in order to find out where we are in that period at time t, we can find that using our t value all over t, right? Our little t all over our period. Now the reason why this fraction works, I'll use it using numbers instead of variables. Let's say our period is now 3 seconds, okay? Just ignore this for now. We're now using period of 3 seconds, okay? Let's say we want to find where the pendulum is at t is equal to 1.5 seconds. Now we know that 1.5 is half of 3. We know that. So we know intuitively that the pendulum should be halfway through its period. And this fraction tells us that. If we sub in our numbers, 1.5 all over 3, that is equal to 0.5, or 1/2, right? So that gives us the fraction of our period that we've gone through, okay, at time t. Now you can see that the x-axis on our graph is not in time, it's not in our period, it's in radians, right? Our theta, it's an angle. So in order to turn this into an angle, we can times it by 2 pi. Right, the reason why that works is because in one period, there is 2 pi radians, okay? So now that we know that, we can sub that into our equation where we have x of t, right, that's our displacement at time t, is equal to a sine 2 pi times t all over t. This equation is exactly equivalent to this equation, right? I know it doesn't look like it. Let's draw that out right here. Let's draw out the other equation, a sine theta, right? It might not look like it at this stage, but you should know from your math courses that we can change this to look like 2 pi over t times t, right? You should know we can make that conversion. And 2 pi over t looks familiar. It's our omega, right? And we know that theta is equal to omega t. So if we replace omega with this and times it by t, we get our theta. So in fact, this is equal to this equation. Now I am fairly certain on your formula sheet it is not in this form. It will say y is equal to a sine omega t, right? And that also makes sense from here. We have our omega replaces our 2 pi over t times t, so a sine omega t. And our y is just another way to say x of t. Same thing. Right, so now that is our displacement sorted. So now let's move on to our velocity. Right? I promise I'll get into reference circles later in the video. I just want to get this out of the way so we have a clear understanding and we can use the reference circle a lot better. Now, our velocity is very, very similar to our displacement equation, right? If, again, we have our situation where we have our pendulum in the mean position and the pendulum is moving left to right. Let's say we imagine the pendulum came from here, So it's still starting at the mean, but it's coming like back. It's coming back around. So it's coming this way. It will reach max velocity when it's in the mean position, right? At that point, it's no longer accelerating and it's at a constant max velocity, right? For like a half a second, like a split second, not even half, less than that, like way less. But it's still at max velocity. So again, we can plot that. So we will have our Vmax, right? So that's our max velocity, and our negative Vmax, right? Now negative Vmax, we remember velocity is a vector, so it has a direction. So we can say that positive velocity is when it's coming this way, and then negative velocity is when it's coming this way. It's arbitrary, it doesn't really matter. The graph is the same, just flipped. Don't worry about that too much. We know that it's coming this way, and I just defined that max velocity is that way, so we start at max velocity, at the mean position. Then we come over here, and we know that when a pendulum is at its max displacement, it is momentarily at rest. So it comes down to 0 velocity. Then it comes back down this way, and it's back at the mean, but at the negative direction. Then back up here to its max displacement again, momentarily at rest, and it comes back up here, and then back at the mean position once again, where it's at max velocity. So it comes down like this, and as you can see, it forms a cosine graph. Now, does that make sense? Now, intuitively, I just explained it makes sense by looking at it visually, but mathematically, we should also know from our level 2 calculus, I think, that if we differentiate distance or displacement, we get our velocity, right? And indeed, if you remember, if we differentiate sine theta, we get cos theta. So indeed, the math does check out. Now again, we have the exact same problem that we had with our displacement function. Just having cos theta on its own is not very helpful, because again, cos theta also returns a value between 1 and -1, right? So we need to multiply it by something to get a scaling factor. We can't just multiply it by its displacement, because that no longer works. What we need to do is multiply it by Vmax. So we get Vmax cos theta, right? And theta can also be replaced by omega t, as we did up here. So we get our velocity at time t is equal to Vmax cos omega t. Now in your formula sheet, you probably have it as V of t is equal to a omega cos omega t, right? But Vmax is equal to a omega, right? Okay, just a quick interjection. This is me from the future. Well, future for me, not future for you. Anyways, I realized when I was editing this part, I completely glossed over why Vmax is equal to a omega, okay? So I'm gonna just go through that. So like I said before, we can get our velocity by differentiating our displacement, right? And I did like a small little example using the sine theta and cos theta. But if we take our full displacement equation, right, a sine omega t, right, and we differentiate this, right, so we get x prime t, or x dash, whatever you want to call it, and that's equal to our velocity we said, and that is equal to the derivative with respect to time of this equation right here, so a sine, and we can put this in brackets, omega t, right? And we should remember that when we differentiate sine, we get cos, right? And also, when we differentiate a trig function, we also need to differentiate what's in the brackets right here, right? So when we differentiate this, we get our velocity with respect to time is equal to a cos, and then the derivative of what's in this bracket. So the derivative of omega t with respect to t is just omega, right? So we get cos omega t times omega, right? And that is equal to a omega cos omega t, our velocity. And as you can see here, that is the same equation we have over here. And obviously our a omega is equal to our Vmax. All right, now finally moving on to acceleration, where we have our pendulum again, once again in the mean position. When it's in its mean position, that is when the acceleration is 0, right? So again, if we have our graph where this is our A max, so acceleration max, and then negative A max. Acceleration is 0 at the mean, so we start at 0 acceleration, comes up here, and then when the pendulum is at max displacement, that is when the acceleration is max, trying to pull it down. Now the acceleration is in the opposite direction to the displacement, so if displacement is this way, the acceleration is down this way. And so we actually go to A max first, and then it comes back to the mean, right? At the mean position, acceleration is 0, comes up to max displacement on the other side, and we get max again, and then it comes back to the mean, where acceleration is 0 once again. And as you can see, we get a sine graph again. However, this is a negative sine graph. Okay. Once again, a sine graph is useless because you guessed it, returns a value between 1 and -1. So we need to multiply it by something, and that is going to be our A max sine theta. Now again, the sine theta is negative, so we need to minus that. Right? So negative A max sine theta. And that is our acceleration at time t. And on your formula sheet, you should also see that A max is equal to A omega squared. And so the equation that you'll see on your formula sheet is A is equal to A omega squared, negative A omega squared, sine omega t. So again, this is me from the future again. I again glossed over how A max is equal to A omega squared. It's pretty much the exact same as the velocity. So we have our velocity equation, A omega cos omega t, right? And we can put this in brackets if we want. And then we differentiate the velocity equation, and that's equal to our acceleration, right? And we differentiate it with respect to time. And we get A omega cos omega t, right? Now, just like previously, when we differentiate a cos function, we get negative sine, and then we also need to differentiate whatever in these brackets right here. And just like before, when we differentiate what's in the brackets with respect to time, omega t, that's just equal to omega. And so our acceleration is equal to A omega times negative sine omega t times omega. And we can simplify that to negative A omega squared sine omega t. And there we go. That is the exact same equation we have up here. And as you can see, our A max is equal to A omega squared. Now remember, all of this explanation is when we assume that the pendulum starts at the mean position. If we go back to wherever it was, over here, when we started the pendulum at max displacement, we got a cosine graph first for displacement. So when we differentiate a cosine to get our velocity, we get negative sine theta, right? And to get the acceleration, we get negative cos theta, okay? So just beware. In this explanation, I went from the mean, but the equations are slightly different when you start from max displacement, okay? I trust that through this long-winded explanation that you can convince yourself that this is true. Now, just a quick little side note, if we look at our displacement equation, we get A sine omega t, and the definition of simple harmonic motion that you've probably memorized by now, because it's in every exam, where in order for something to be in simple harmonic motion, the displacement needs to be directly proportional and opposite to the acceleration. Well, you can see here that the displacement is proportional because they're both sine graphs, and in opposite direction because of this negative to the acceleration. So the definition is also within the equations. So now that we got the basics of the trig functions out the way, we can now use the reference circle. In order to use a reference circle, we first obviously need a circle, so we can draw that out. Now remember, we're using the example of the pendulum at the mean position, right? And this pendulum moves from left to right. So we are going to put a line in the middle that goes from left to right. Now we have our midpoint, that is our mean position. And so over on this side, that is our max displacement, or our amplitude. And this is our negative max displacement, or our negative amplitude. Because we're starting at the mean, we can start at the bottom of the circle, and when we do reference circles, we always go anti-clockwise. Okay, now let's say for this example, the pendulum moves through 0.7 meters. Okay, and we want to find what is the velocity at that point. So what we can do is we can trace down here, and we see that the pendulum has moved through this distance on our reference circle. Okay, now we can add a phasor to our reference circle. You don't need to know these names, irrelevant, just an arrow that points to where our new point is. Okay, and we have an angle here, theta. It is indeed the same theta that we have, where is it? Somewhere. Here. That's the same theta. Okay? This length right here, our radius of our circle, is equal to the amplitude, right? So this length right here is equal to our amplitude. And I said in our example, I think, that the amplitude is 1.4 meters. Okay? So we can take this line and trace it down here, and that is 0.7 meters. And as you can see, we got a nice little right angle triangle going on here. Okay, so we can draw that out over here to make it easier to see. And we have 1.4 meters. Okay, the 4 and the m have combined, don't worry about it. And that is 0.7 meters, and that is our theta right here. So we have the hypotenuse and the opposite side, so we can use our inverse sign to find our theta, where this is 0.7 all over 1.4. And that gives an angle of pi over 6. Okay? So now that we know that angle, we also know that theta is equal to omega t. So we can find the value of t. We can say that t is equal to theta all over our omega, and we also know that our omega is equal to 2 pi over t. And I said before that our t is equal to 0.8 seconds, right? So t is equal to pi over 6 all over 2 pi over 0.8. And that gives a time value of 1 over 15 seconds, right? And then from there we can use our equation that we found, where v of t is equal to vmax cos omega t. Right, we know our Vmax again is also a omega, and so that means our amplitude again is 1.4 times our omega, which we get is 2 pi over our period of 0.8, and that is equal to roughly 11 meters per second. And so we can plug that in. 11 times our cos, and omega is again 2 pi all over our period, 0.8, times our t, which is 1 over 15, and that gives us a velocity at time t of 9.53 meters per second. There we go. And if you want, you can also find the acceleration at that time. You can do that yourself. I will give you the answer so you know you're right. And the answer for the acceleration is absolutely ginormous. It's a negative 43.18 meters per second. Just insane value. That is not realistic at all, okay? Keep in mind, gravity is 9.81 meters per second. Right, again, the negative in that scenario is just saying that it's in the opposite direction to the displacement, right? Okay, so another example that we can have for simple harmonic motion is when the displacement is vertical, okay? So that the way we use the reference circle in that scenario is slightly different. So we can have a mass on a spring, right? This is a spring right here. That's a spring. And let's say we pull the spring down. So we pull it down to its max displacement right here, okay? So this is going to be the mass at max displacement. And we can say the amplitude is equal to, let's say, 1.2 meters. And the period is going to be, let's say 2.8 seconds, okay? This is a massive spring, by the way. That's ginormous, right? Imagine the amplitude is 1.2 meters. Insane. Okay. Let's say for this, we want to find when the mass is 0.4 meters above the mean position, right? Above the mean position. So that would be like right here. How long does it take for the mass to be right there? Okay. And also let's find the velocity at this point. Okay. So we can do our reference circle right here. And because we are doing vertical displacement, we can put our line like this. And I will also put a line over here. Okay. So we are starting at max displacement. So we are along this line, and at max displacement, we are at the bottom right here. Okay. And we want to see the time taken to go 0.4 meters above the mean. So this is the mean position. So 0.4 meters above it will be like right here. And then if we trace that over here, that is where we are on the reference circle. So we can draw our phasor like this. And you can see we have an angle right here. Let's call that angle phi. Now, if you remember back to our other example, the angle theta that we're trying to find is actually this entire angle right here. However, that is pretty hard to find. But because we have sectioned off this reference circle into quarters, we know that this right here is 90 degrees. So theta is equal to phi plus 90 degrees. Or because we're working in radians, theta is equal to phi plus pi over 2, right? 90 degrees is pi over 2 in radians. So now, in order to find theta, we just need to find out phi. And as you can see, we have a triangle right here, so we can redraw that out here to make it bigger. And this is our phi. And this distance, we said, was when it was 0.4 meters above the mean. So this is 0.4 meters, meaning that this is also 0.4 meters. And if you remember from our other example, the radius of the circle is our amplitude. So this is 1.2 meters. So we can label that on our big triangle, 0.4 and 1.2 meters. There we go. So we have our opposite side and our hypotenuse, so we can use the inverse sine relationship to find 0.4 all over 1.2, and that's equal to our phi, and our phi is equal to 0.34 radians. And so therefore, our theta is equal to 0.34 plus pi over 2, and this gives us a theta of 1.91 radians. Okay, so now that we have our theta, we know that theta is equal to omega t, and so t is equal to theta all over our omega. We remember our omega is 2 pi over t, and our t is given as 2.8 seconds, so we can make that substitution as well. And we get 1.91 all over our 2 pi over 2.8. This gives us a time of 0.85 seconds. There we go. Now we want to find the velocity. And if you remember, we started from max displacement. So in our example that I did for our velocity, which is up here, this is when we started from the mean. However, like I said previously, our graph looks slightly different when we start from max displacement. So I'm gonna go through that just so you get a understanding. When the mass is at max displacement, it is momentarily at rest. So at max displacement, the velocity is 0. So we actually start at 0, and this is our Vmax, remember? And then we have negative Vmax. Okay, so we start at 0. And then when the mass moves back up, so let's draw the mass again. Mass moves back up, and then it's at the mean position. When it's at the mean position, then the velocity is maxed. So we go up here, then it goes to max displacement again, velocity is 0. Then it comes back down to the mean, so negative Vmax, and then back up. And as you can see, this follows the shape of a sine curve. So this time when we use the velocity equation, we're using the one with the sine in it. So a omega sine omega t, okay? And so we can sub in our values, and we should get an answer of 2.6 meters per second. There we go. So, in my opinion, understanding the trig behind the equations that we use in simple harmonic motion is the key part to understanding reference circles. From there, using the reference circle itself is purely based on practice. So there are plenty of past papers, I'm sure, that use the reference. There are plenty of past papers that use reference circle. I'm not sure if I used the reference circle when I went through the exams. I don't think I did. Okay, that's probably not good. But in my opinion, using the reference circle is easier once you know what you're doing. Okay, to reiterate, understanding these trig functions and how they come about is, I'd say, 90% of the work to understanding reference circles. And yeah, that'll be us for today. See you.